Oh, Professor Brandon, I have one question for newly imagined technologies. Now, as you said, we have a lot of newly imagined technologies to detect damages in our brain, and you can also see the brain activation when we are doing experiments. And you have talked about the lighting up of the brains, and you also said our experiment is not just about the lighting up of the brains. So I'm I'm thinking, what else can we use to explain the phenomenon we observed except the activated brain area?
Hmm. Well, there's a number of ways that we've always traditionally tried to understand how the brain works before we had any neuroimaging. So there was no lighting up at all. It's only in the last 30 or 40 years that we've been able to make sense of the brain using technology. But before that, we used different methods that we call lesion-based methods. And I explained some of these to you in the first lecture. So, for example, Paul Broca, he studied the brain of Tan, who had lost a specific part of his frontal lobe, Brodmann's area 44, 45. We now call that area Broca's area. When we look at those, what we call lesion studies, then we see that without that area of the brain, the function of speech is lost. So we can infer that the area that is lost is necessary for the production of speech. But it may not be sufficient for the production of speech. There may be other parts of the system that are also used. So, in order to understand the difference between what is necessary for a particular function and what is sufficient, we need to have more powerful neuroimaging techniques. In the case of lesion study, all we know is what's necessary. We don't know what is sufficient to perform a speech act. We know that without Broca's area, speech acts are not possible, but we don't know if that is the only sufficient area that is necessary for speech, so that other areas that are not damaged may also be involved in speech, but we would not know that by simply examining Tan's brain because those regions are intact. So the logic of the lesion study, which is simply to look at what's lost, doesn't tell us what else may be involved in the speech act itself. To understand that, we need to look at fMRI or similar techniques which can tell us, well, when speech is engaged in the brain, which areas are in fact showing activity. We can presume that Broca's area will be one of those regions, and in fact it is. So Brodmann's area 44, 45 will show activity, but other areas also show activity. And to understand that those areas are involved in speech, we would have to use neuroimaging because to study the brain of a patient with a lesion would not be enough, would not be sufficient to tell us that those other areas were also involved.
So it's better for us to involve two methods, lesion and newly imagined together for us to help us to detect.
Hmm. Well, traditionally, the lesion approach has been the only available approach for neurologists to understand the relationship between brain and behavior for many hundreds of years. But in the case of brain imaging, um, we do get additional information, but we don't have all of that information um, um, directly available to us in the case of particular types of cognitive function. So, for example, reasoning, conceptual processing, these are very abstract cognitive processes which we don't easily identify with brain imaging. Take, for example, the process called theory of mind. This is a process, cognitive process, which we know is necessary for us to communicate. So when we speak, I speak to you in a directed way because you've asked me a question, so I can infer from that question what is the intention of your question and what's in your mind at the time you ask the question. But in other cases or other circumstances, I may interpret what is in your mind without hearing a question. I may think what is in your mind because I appreciate that you have your own mind, and therefore, in our conversation, I can infer what you are thinking from what you are saying. So, the ability to theorize about another person's mind or mental activity is called theory of mind. In the case of patients who have frontal lobe pathology, or more specifically, children with autism, a kind of childhood language disorder, we know that children with autism and adults also do not have a full appreciation of another person's theory of mind. And that creates certain communication barriers. So, if in a normal conversation I can infer a great deal about your intention when you speak, if I understand what's in your mind reasonably well, and you tacitly agree with that, people with autism cannot make inferences about what is in another person's mind. And so they will often literally interpret what people say and cannot benefit from their understanding of what might be the intention of another person's speech. The point of this is to say that with fMRI, we cannot find the area of the brain that is used for theory of mind. It's not possible to do that. So we can't say theory of mind has a specific brain location. We do know that on a theory of mind task, different areas of the brain will be active, but we can't reduce that activity to any particular region. So we don't know what's necessary for theory of mind. And we've never come across a patient in the neurological literature who loses theory of mind only. In the case of speech, we have found cases where speech only is impaired and everything else is preserved. In the case of theory of mind, we have never found a case where only theory of mind is lost. So without that lesion, we don't know enough about the full story of theory of mind. So there are limits to both the lesion studies and the fMRI studies, which mean that we do need as many different points of reference, sources of evidence, to be able to determine what's necessary and what's sufficient for a cognitive process.
Is it possible for us to have a kind of neuroimaging technology to visualize the cognitive processing, just as you said, mind reading?
Oh, no. Some people argue it is possible to activate regions of the brain that are sensitive to empathy. So those studies are not conclusive. But perhaps the most interesting answer to your question would be to look at a very simple process, such as what we call imagery. This is where we have the ability to imagine in our minds the change of shape of an object. We can mentally rotate objects in space in our minds without seeing them in front of us. And we can answer questions, about what's bigger, a flea or an elephant. We know an elephant is bigger, but why do we know that? Possibly because we bring an image of an elephant and a flea and we see one is bigger than the other. So the idea is that we use imagery for a lot of mental processing, a lot of cognitive processing. And when we do studies of people who are imaging in that way, performing tasks like rotating objects, answering questions about elephants and fleas, we see that the brain is showing more activity in the visual cortex, the back of the brain. Now, that's pretty strong evidence that when we are doing these imagery tasks, then we are engaging those areas that are ordinarily used for visual processing. So, in some sense, we are mind reading by using the mental rotation, but doing it using our visual system. So, there is a kind of ability to be able to abstract away from the real world through imagery, that is using the material of the brain that are the sensory systems that we are required to do the real perception of space. So there is an ability to use imaging to illustrate how something as abstract as imagery can be processed in a physical way in the brain.
Does animal have the same kind of mental imagery?
Does everyone have the same kind
Animal,
of animal?
yes.
We don't know because we can't ask animals question about rotating object or question about fly and elephant. So we don't know.
Okay, thank you.
Okay.